Welcome everyone to today podcast. We have special guest. I'm Muhammad Swilam, and in this episode we will learn a lot from our lovely teacher Neal Ford. Neal is the co-author of Fundamental of Software Architecture and Building Evolutionary Architecture and many other landmark books. Actually, they shaped how we work today with modern software architecture and software in general. Today, we will be diving into real problems. We would like to bridge the gap between the software architecture and some of the real problems that we face today. Neal, it's a pleasure to have you.
Great. It's a great pleasure to be here. Thanks for having me.
Thank you so much. Neal, to warm up, I would like to ask you something about your few last years. What has changed since Fundamental of Software Architecture?
Well, not much changed actually since the publication of the book, because we took almost 10 years to build all the material to write the book. So this is actually one of the things that Mark and I have sort of innovated is the sort of iterative process for writing books. And we've done this several times. We're actually in the process of doing that now, because when the seed for the fundamentals book was I saw a salary survey on some magazine or newspaper or news station or something that talking about desirable jobs in that particular year, and software architect was one of them. And I thought, oh, that's interesting. But then I looked at all the other jobs on that list, like nurse practitioner or pharmacist, and there's a very clearly defined career path from not being a pharmacist to being a pharmacist. You know, there's an easy path that you can easily look up, but that's not true for software architect. There's no really good, clear fundamentals book about what we do as software architects. And so it turned out that Mark and I were both speaking at the same conference. Mark Richards, my co-author, were both speaking at the same conference series, and he and I were both doing talks about software architecture. And so we sat down at one point and said, you know, what would a workshop about software architecture look like? And it's like, well, it would be weeks. Well, how can we distill it and basically come up with the things that you absolutely have to know? And then we did that workshop for several years until we had refined it to the point where we could actually write it down into a book. And so a lot of the book is the sort of distilled version of, you know, all that material, sort of what are the absolute fundamental things, because software architects is one of those roles where it can grow infinitely large depending on the responsibilities in an organization, depending on roles that are partially filled by other people but have to be solved at the end of the day. And so an architect takes on some of those things. And so the real trick there was not delineating everything that we do, but finding what is the least common denominator of what we do. And so since the book came out, the biggest change probably has been that we're not trying to build that material anymore. We're building different material. But I think one of the things that book indicated that has been a strong sort of thread throughout my books that even predates that, because the first edition of Evolutionary Architectures came before the Fundamentals book, was this idea of our subtitle of our Fundamentals book, which is an engineering approach to software architecture, which really means concrete measurement as much as we can and feedback. And so it's a lot of that is, can you take the same principles that other engineering disciplines use, but apply those to software, but not in identical ways, but in purposeful ways? And I know that sounds confusing, but let me explain what I mean by that. I had the very beginning of my career, I was one of those people that majored in a lot of things. My first major was actually journalism, which thankfully I did not finish that major, but that's where all the writing comes from. And I was a biology major for a while, but my 2-year degree was actually toward a mechanical engineering degree. And that's when I started my college career. My university career was actually mechanical engineering until I'd had enough of that to realize I didn't want to do it the rest of my life. But I did get a whole lot of calculus and the engineering math, and I realized that, wow, they have a lot of math in mechanical engineering. And boy, wouldn't it be nice if we had that in software, the same level of math. But then I realized at some point, this is actually because of an influential essay about design and software, that we don't actually need that. That's not our engineering rigor in software is not in building calculus to predict what software is going to do, because we have one key advantage that mechanical engineers and building architects don't have. And that is we can build it with almost no effort and then change it with almost no effort. Software is soft on purpose. This is actually the insight of this great essay about design, that the real design in software is not the lines and boxes, it's the source code. We can change that design on the fly just about any time and verify that it's actually working. And so that's what I meant by that vague phrase that I said earlier, is that an engineer wants to have ways of validating their design. Mechanical engineers and architects validate that through calculus and mathematics and a lot of heavy-duty math. But as software architects and developers, we validate things by building it and then verifying that it is working the way that we expected it to. And of course, that is where testing comes in. That's where this idea of architectural fitness functions come in, this idea of creating feedback for our design to see, is our design working correctly? And in fact, that's the basic theme of the book that I'm working on with Mark right now, which is Architecture as Code, is how do you build more of those kind of feedbacks into your ecosystem?
Perfect. Neal, but I have a question regarding the practical approaches you take. Nothing of them come without practice. And you, as a big software architect, are you still trying yourself?
Oh, sure. I'm still a consultant by trade. I'm still paid as a professional consultant. So I still work on projects. Most of my work now is advisory work for, hey, we have this design, we're trying to solve this difficult problem. Here are 3 ways we thought about solving it, which is the better way to solve it. And so that's a lot of what my work looks like now. But I am still involved in professional services because I work for ThoughtWorks, which is an international consulting company. So the advantage of that, and in fact, always the advantage that I tell people about being a consultant, so, every superpower comes with kryptonite. So the superpower of being a consultant is that you get to see lots and lots of different projects, different scenarios, different ways of solving problems, and you can kind of see which ones work and don't work. That's where all the book writing comes from, because you can pattern match across a lot of things that you've touched and seen similarities and differences and derive examples. The kryptonite of most consultants is that we rarely see things from the very beginning through its maintenance and life cycle, through its end. And so we rarely live with something for 10 years, a piece of software. We're more likely to be intensely involved with a piece of software for a year or 2 years or something like that, and then move on to a different one. And so, but that's the way my career has always been. In the very early days when I was at ThoughtWorks, I was working on more sort of very long-term supervising, mostly distributed agile projects where some developers in the US, some were in India, sometimes in South America. And gradually over time, as my role has changed, it has become more sort of advisory work on projects like what it mostly is now. And even that is schedule dependent, because it turns out the way my schedule works out is I'm very, very busy traveling for conferences and related activities in the spring and fall, and my summer and winter are much more free. And so I tend to do more heads down project work in the summer and winter than in the spring and fall, which is a lot more traveling around from suitcases.
Okay, now moving to maybe one of my special concern is around architecture decisions. And the problem I always see, teams hesitate to take early decision because they know the business context will change. Do you think we can have a technique that help teams to take a decision at early on stages?
Well, so all we really need is a working crystal ball and the ability to be able to tell the future. As soon as we get that, then all of our problems will be solved. But we don't have that. We're never going to get that. So this is always going to be a problem in software when you don't have a well-defined problem yet, and it can change. So building software is by its nature exploratory, because when you're building a piece of software, you're building something that no one has ever built before. If you've already got one, then you can just create a copy of it because it's a digital thing. You can create as many copies of it as you want. So by definition, nobody's built the exact version of what you're building for, which is also by its definition exploratory. And in fact, We want to encourage that sort of emergent design. As we learn more about the problem domain, we'd like to be able to fundamentally change the things as we build it, as we learn more about it. What we don't want to do is make some very strict decisions early on that prevent us from actually modeling the thing as closely as possible to the real world scenario. And so this is a famous distinction that my co-author, Dr. Rebecca Parsons, made of emergent design, which you want to encourage on projects. In fact, a lot of the design techniques lean into this idea of letting things emerge over time, but you cannot emerge architecture. And this is the fundamental problem that your question is getting at, is because architecture is about, so this is a distinction that we really only came around to, and even after the fundamentals book, when we were writing the Head First software architecture book with Rajiv Gandhi, one of the things that we realized is you can sort of split structural design and architecture into behavior and capabilities. Capabilities are what a lot of people call non-functional requirements, or we call architecture characteristics, or that's where the ilities thing comes from, is they're describing capabilities. And so you can think about behavior versus capabilities. We want to evolve or emerge behavior because that's the reason we're writing the software. But you can't emerge capabilities because, for example, a very small thing cannot be as scalable as a very large thing because that's a capability, not part of the behavior of the system. But that's where the ideas of evolutionary architecture come in. The idea is that you build a system now with the best knowledge you have right now, but build it in such a way that you can relatively easily change it and evolve it toward some future goal, whether it's a mysterious future goal or some likely future goal. For example, we're building a system now that has really strict time to market. And so for that and several other reasons, we're going to build it as a monolithic single system because that'll make it a lot easier to build it more quickly. But I want to build it as a modular monolith, not a layered architecture, because if it does become successful, I would like to migrate it to microservices. Well, being a modular monolith means I have the same kind of internal partitioning as I would in microservices, so that makes the migration path much easier. So that's what I'm talking about, is a sort of low-cost future-proofing, a decision like that where I'm making a decision now based on my current constraints, but then realizing what constraints may be coming and some future proofing for that. Although the danger of that, of course, is trying to design for something that never comes about. And now you're over engineering and you're paying a constant price for that thing and getting no advantage from it. If you would like, and I encourage our listeners to go look at this, if you're curious, Barry O'Reilly has been involved in this very interesting project, which is trying to address exactly what you're talking about, is how can you predict the future of design in your software architecture as you build it? And he's been working on this thing called residuality theory. So if you look up residuality theory, this is based on complexity science and some other interesting sources where he's suggesting that basically a different level of modularity in architecture, of this idea of a residue, which is a combination of, it's sort of what we call an architecture quantum, which means it is, a scope for architecture characteristic and coupling. It's a little broader than that, but the idea is if you design those correctly, then when future similar problems come along, you've already solved them. It's an interesting idea. He's still working on it. I encourage him to keep working on that. One of the basic premises that he has is that software systems behave mathematically like other complex systems in terms of things like Monte Carlo distributions, et cetera, in terms of the choices we make. And I'm not quite sure that's true because they're more constrained than that because of the forces you were talking about. The business makes a decision, changes their decision or changes their mind about something. We decide to merge with another company. Those kinds of things are much harder to quantify, I think. But anyway, there are efforts involved in doing that. We are actually touching on residuality theory just a little bit in the book we're working on now, because we're writing this book about all these different intersections in architecture, and these intersections are good ways to think about and find potential residuals. So
you encourage starting simple and moving towards whatever objective you want by exploration itself.
Yes. Well, particularly from a behavioral standpoint, there's a limited amount of that you can do with architecture. I can't start with a very simple, non-scalable system and then gradually make it scalable. At some point, I have to stop with that simple system and build a brand new system that is actually scalable. Now, I can evolve that system, but it's much more difficult to do that than take a simple behavioral system and then add more behavior to it over time.
I saw before actually some companies working like this, and they started with modular monolith to build a microservice. But actually they ended up building a modular monolith and they call it microservices.
Well, you can call things anything you want. Nobody's going to come and give you a grade as to how well you've done your microservices in your organization. So I've seen a lot of architectures that aren't actually microservices, but they call them microservices because that's what all the cool kids are doing. I tell people, I don't care what you call your architecture. If it's solving your problem in a concrete way and it's making things better, then you call it whatever you want. I would call it success. That's the only important.
But lesson learned, maybe. Lesson learned, did you observe specific patterns that companies use it, or maybe a pitfalls that the company go towards and they end up with this? But starting for microservice and they end up with modular monolith?
Well, the problem if you start with microservices is you don't end up with a modular monolith, you end up with a distributed ball of mud. This is actually an anti-pattern that we call the grains of sand anti-pattern. And it comes along with a similar anti-pattern called the swarm of gnats anti-pattern. Grains of sand, as I built microservices, that are too fine-grained. And now the entire performance of my architecture is nothing but communication overhead between services trying to do useful workflows. Latency ends up killing the entire performance of your architecture. That's too fine grained from a granularity standpoint. The swarm of gnats is I'm generating so many messages in my event-driven architecture, and some of them are, so many of them are useless that it's just like swatting gnats away. There's just too much going on for me to make decisions in that architecture. So
when we talk about software architecture and you would like to act as a consultant, as you mentioned, for some legacy systems, it's not only about software architecture, it's also about the team. So you architect for flow for sure. So if we didn't have the flexibility from the company of doing this, because, as a software architect, I can guide the development team how they should build the software architecture. But again, team dynamics, we need team dynamics. How can I convince the company that we need to, for example, restructure the org?
So one of the intersections we're talking about in our upcoming book is the intersection of architecture and team topologies. So it's actually good that we have ammunition now in terms of the book, Team Topologies, because it really describes. Now, Team Topologies is a bit biased toward domain-driven design and microservices and modern distributed architectures, but it does a really good job of delineating some of the impacts that structure has on the way that you build things in your world. But a more general answer to your question is something that goes back to something I was saying earlier about an engineering approach. And one of our favorite things is demonstration defeats discussion. Stop talking about it. You're never going to convince anybody by talking about we are misaligned as an organization. That's going to fall on deaf ears. You need to find evidence in your organization of how that's causing problems. So, for example, one of the common misfunctions that we see in organizations it's very common for organizations to seat people by job responsibility. All the presentation people sit in one place, all the data engineers sit in another place on a different floor, all the developers sit in another place on a different floor. And that actually makes sense in terms of Conway's law if you're building layered architectures with a presentation layer and a business rules layer and a data access layer. But if you're building something like microservices, all you're doing is creating a huge amount of interlayer communication between all those floors. And we've seen that cross-functional teams actually work much better split the teams and responsibilities around the kind of thing that they're building. Well, I need evidence of this. And so now look at, to build a new feature in your organization, how many tickets does it take to build a new feature if we're all sitting in different places versus how much would it take if we were all co-located? And create a co-located team and actually measure the amount of inter-team communication and what method it uses. And what you'll see is that by separating people by technical layers, you're creating a tremendous amount of communication overhead, which is really slowing down your software development process. It seems efficient to stick all the like people together in an organization, and it's certainly a lot easier to, from the building manager standpoint, but you've got to measure what kind of impact is it having on productivity, and maybe even create pilots to try alternatives and measure those as well. It's much harder for organizations to argue against real data, particularly data derived from within your own organization.
So you will start first observing the signals and consolidate a report and start immediately discussing the report.
Sure.
So talking about data. Okay. Would we need some proof of concept for our recommended approach to convince the whatever stakeholders we are talking to?
So what I would do is take supporting data for what you're trying to get around to, like, for example, our teams are mispartitioned because every time we touch this, it impacts 5 other teams. That seems bad. So start with the data and then suggest an alternative and then measure that to see if it's better than what you're living with. Because who knows, it may make it worse. So, but you want to measure, you want to know. That's the key here, is measure as many things you can. That's that engineering approach to software development. We can learn so many things in software projects that we're just not taking advantage of because we're just not harvesting the data for it. And so look at the existing ecosystem and then suggest, okay, I recommend that instead of using a shared component for this, because every time somebody changes it, everybody has to recompile their services, we should change that to a shared service. Okay, what are the trade-offs of doing that? And now let's actually see how that would impact each team that needs that shared functionality. So that's gathering actual data, from your real ecosystem.
We can build good architecture if we follow the principles and the science behind this architecture, but the big problem I always see is data coupling. So we build the architecture correctly, but we start to face multiple issues related to data coupling and the data ownership. Do you have a good approach that we can follow that can govern this data boundaries and ownership?
Yes, stop treating it as something separate, because it's not. This is the great insight that Eric Evans had in domain-driven design. It's not somebody else's problem, it's your problem. It just turns out it's a complicated problem. Well, life sucks sometimes and gives you complicated problems you have to solve. So that's one of the side effects of this whole philosophy of bounded context in microservices, is this, I believe, entirely accurate observation by Eric Evans that your database schema is every bit as much of an implementation detail as your code. Turns out it's really easy to manage dependencies and things like that between code, because we've been building the mechanisms to do that for decades and decades. It's a lot harder to manage those things between data, but that doesn't reduce the reality that it's as much an implementation detail as your code. And so you just have to figure out ways to deal with it. Now, having said that, we're working on some of those things as well for example, referential integrity. But we're used to having that supplied by a database, but you can build that yourself within a distributed architecture. You just have to write it yourself. It's just not magically supplied like it is in a database. And so a lot of these things, these capabilities are possible. You just have to think about and actually build those things.
But when modernizing a system, one identifier in another system can make a big issue in the whole system. So
which is why coupling is bad, whether it's source code or whether it's data. And so you should take the exact same approach you would take in code and build anti-corruption layers between the data. This is where the ownership versus who can read it versus who can own it argument comes in microservices all the time. Problem you run into, of course, is if you're trying to manage your data as if it were not a distributed architecture with foreign keys and referential integrity, but you're trying to build a distributed architecture, you got a misalignment there. That's like trying to build a monolithic front end and building a microservices back end. You're going to end up with the disadvantages of both and the advantages of neither. The same is true if you're trying to build an intensely distributed microservices architecture, but you want to rely on a monolithic database and all of its facilities, like referential integrity and foreign keys and all those sorts of things, then you're going to get the disadvantages of both. Because you have distributed services where you're taking all the communication overhead of them talking to one another, but you don't have the scalability or availability independence of having independent databases because you just have one. So the real trick there is to find out, how do I reconcile the data dependencies just like I would reconcile code dependencies? Now, one of the common ways we do this, in fact, we talk about this quite a lot in our Software Architecture, the Hard Parts book, is to use things like in-memory caching. I'm catalog and I need product information. I don't own that, but I need it. I don't want to do an inter-service call every time I need to reconcile a catalog ID with the catalog description. So what I'll do is on startup, fill up a cache with all my item IDs and catalog descriptions. And now I have an in-memory data store of those things that I don't own, but I can read as I need to. And so caching is used a lot to look at information I don't own, but I need access to in a scalable way in a distributed architecture. But the data dependencies, this is in fact one of the things that we identify as what we call an integrator that makes it really difficult to break things down into smaller and smaller pieces. In microservices, very often data is the constraint. That means I can't break it down any smaller because I absolutely have to have these data relationships preserved at the database level. So it's a common limitation in these kind of distributed architectures.
Okay, you and Dr. Rebecca, I think, already champion of evolutionary architecture and fitness function. Although it's very interesting, I would like to ask you, how can we apply it without showing slowness in delivery?
It's a great question. And in fact, this is mostly what this book we're working on now, Architecture as Code, is about. But one of the, I just did a talk, in fact, at an AI conference in New York about 2 weeks ago that addresses this exact problem. One of the problems we have traditionally had when we try to take this concept of architecture fitness functions. So this is like referential integrity is a great example of that. I want to build an architecture fitness function. I have these two databases in distributed architecture, but I want to make sure that I never have tickets that don't have customer keys. I want to make a foreign key data consistency between those two things so I can build a fitness function that basically says, look at the two, do a query in the two databases and make sure that there are no stray keys from tickets to customers. I can build that code myself and do that. But that's very much at the project level. As an enterprise architect, I would like to ensure throughout the organization that every project that's doing data has referential integrity, that has data consistency across the project. But here's the problem. As an enterprise architect, if I try to write that fitness function, I have to know a lot of details about how they are implementing that project. We're using the term now meta-bounded context. So in domain-driven design, in this idea of a bounded context, all the implementation details within a bounded context are secret, and you build these anti-corruption layers to the outside world. What that allows you to do is change the internal implementation without breaking any of the collaborators to this bounded context. We can think about that as the software project level as well, what we're calling a meta-bounded context. Because as an enterprise architect, to be able to write that referential integrity fitness function, I would have to know what the databases were, what the columns were, et cetera, a lot of implementation details. And those things are going to change as they evolve that piece of software. That's where MCP comes in, the Model Context Protocol in the agentic AI world. So MCP is a standardized protocol that allows agents to talk to one another. And there are basically three calls you can make to it. One is, what tools will you provide for me that my agents can call? what data sources will you provide for me that my agent can take advantage of? And what prompt libraries can you provide that will coordinate some sort of work on your behalf? But it turns out MCP is fantastic for this idea of fitness functions and knowing too many implementation details, because now I can set up an MCP server at the project level, and it has a tool that it supplies the outside world that says validate referential integrity. And at that project level, it knows exactly what databases are involved, what columns are involved, and how to do that comparison. From an enterprise architecture level, I can call their MCP server and say, validate referential integrity. That's my intent, and it will handle that for me. At some point in the future, when they change the internal implementation and add a third database, they change the way their MCP server reacts to that call, but I don't have to change my call as an enterprise architect. And so this is one of the ways, to go back to this a long answer to your question, to prevent fitness functions from slowing things down. Because ultimately fitness functions, every time they break, you have to stop and fix something. And you want those breakages to be because something that I care about has broken, not something, some accidental complexity like, oh, someone has changed the implementation of something and I need to update the fitness function. This gives you a way, another level of indirection to remove some of that incidental breakage and only break when it's important that you break. Now, fitness functions in general do not break as often as things like unit tests or functional tests, because those are modeling the thing you're writing your software about. And that's the thing that's most likely to change most aggressively. Fitness functions don't break as often, but we also want to insulate them from breaking for reasons that are just adding churn and not value to the project. And so using MCP as an extra level of indirection gets rid of some of that incidental churn.
But where would you set up the MCP? On the local machine for the developers or on the CI server, for example?
Probably the CI server for the project. It needs to be somewhere local to the project scope, and it needs to have somewhere that you have access to the build state of the project. And so the CI server deployment pipeline would be the obvious place to put that. But for the code that actually does the validation for you in runtime, you'd more likely put that actually in the service mesh. So it's quite common for microservice architectures to use a service mesh to manage things like monitoring, logging, service discovery, authentication, authorization. Governance is just another thing you can wire into the service mesh. And it can do things like when this queue depth reaches 0, meaning there are no pending messages, compare these two databases to make sure they're consistent. I can build that into the service mesh, and so it can be wired to every time this event occurs, do this validation check for me. And of course, that could be insulated with an MCP server as well, so I don't have to know the details of that.
What I'm thinking of, we usually use this CI server before doing the actual build. It's just a step in the way to the build. So now if we introduce the MCP server, we need also to allow the MCP server itself to reach some other system to check the integrity validation, right?
Well, so the way I envision MCP server is much more of a receiver than a sender. I want an MCP server at the scope of my project that can receive requests from the enterprise architect's agents. As an enterprise architect, I'm going to create an agent that says, validate the referential integrity for the databases in my distributed architectures. And it's going to make a call to the MCP server for your project that says, hey, look at your databases and validate referential integrity. So I don't anticipate MCP servers at the project level reaching out and doing all this adventurous stuff. Instead, as basically building a standard API where roles like enterprise architects can call to ask it for data sources. I wouldn't even have to build a validation tool. I could just say, give me the two data sources I care about and do the comparison myself. That still insulates me from changes, because if they change the internal representation, but don't have to change what returns from the MCP server, then I haven't broken my fitness function.
When we talk about system governance and architecture governance, what I really like about fitness function, where we have it in a central place, so no one can change it, and we have some kind of enforcement. But But on the local side, engineer can simply ignore it, right? Or can even disable it.
That's true for any kind of testing. It's true for any kind of security protocol. It's true for anything in software.
Would you like to have this always in a central place away from the project source code instead?
Well, so what you're really suggesting is, can I build a police state as an architect where nobody can violate my rules? And if history has taught us anything, is that there's no police state so sophisticated that clever criminals can't figure out a way around whatever you set up. You're much better off gathering cooperation versus enforcement. You have to explain to people, okay, this fitness function is there for a reason. It's not just to make your life miserable. It may seem like that, but that's not the purpose. It's the purpose for that thing to be there is so that we can keep building on this thing as a solid foundation. Because if we allow people to keep chipping away micro cracks in the foundation, eventually the whole building falls. And that's what the fitness functions are there for, is to prevent the little micro cracks from happening in the foundation. So there are a couple of things about that. One is you need cooperation from developers, because architects write these things, but developers are ones who trip them and fail them and have to go to extra effort to make them pass again. So you don't want them to be mad at you about that. The other thing about them is you don't want too many of them. In fact, one of the things that we're arguing in our architecture's code book is that architectural fitness functions should not be as comprehensive as unit tests. They should only be for high value things. So the problem is, if you write a fitness function for every little thing, they're going to break a lot, and it's going to create friction and frustration a lot. And if it's not a high value thing, then you're wasting a lot of your capital as an architect. They are willing to put up with some level of hassle for architectural governance, but at some point it becomes just too much hassle. And so you're always playing in that area. And so I think it's much better off to set up an ecosystem where developers don't mind fitness functions breaking, because it's feedback. Don't think of it as a test. Think of it as fast feedback. That's the other thing that we're arguing in our upcoming book, is that fitness functions are not actually test failures. So when a unit test breaks, it's something bad has happened. When a fitness function breaks, it's really just a feedback opportunity for, hey, something changed. I want to look at that change. For example, if you build a structural fitness function that says, these are the only components I want in my system, but then somebody creates a new directory as they're building a solution, they've actually built a new component. Most of the time, you wouldn't even notice that until it's in production, and now you've had months of work built on this new component. If you've built a fitness function that's looking for anything outside of the components I've defined, you get immediate feedback that, oh, look, this has changed. Now you can ask the question, should we have this extra component, or was that a mistake? That's what fitness functions are really for, is a way of wiring in super fast feedback for something important has changed, and I want to know about it so I can make a decision about it.
Awesome. Okay, now moving to the human factor in architecture. Usually, architecture often hides some culture problem. And I do believe, Neal, you observed this tons of time. What techniques would you recommend for software architects to get buy-in, even without authority?
Well, I think the best way that you can get buy-in is to not be an evangelist for particular approaches or anything like that, because you're just going to end up irritating some people and getting other people excited for you. The real skill, and this is what I tell beginning architects at ThoughtWorks all the time, is your job is not to find magic silver bullet solutions to problems, because they're not common. Instead, it's to become a really, really good objective arbiter of trade-offs, because that's the real job, is doing trade-off analysis. These two competing solutions, which one should we pick and why? Being able to answer that question in a convincing, data-driven way shows great value in an organization, and people start listening to you regardless of what your title is, if you are the go-to person for good objective trade-off analysis. So find, good boundary cases that other people are not thinking about, and do a rigorous analysis, build spreadsheets and matrices comparing these things, and become the go-to person. And then, it's been my experience that it doesn't really matter in a lot of organizations how you got to that information. It's what you're actually saying. This was actually something that we did. This is public record now, but we couldn't talk about it at the time at ThoughtWorks. This has been more than a decade ago. We were brought into Google to work on a bunch of their stuff and to do advisory work as consultants. And we, at Google, at least at that time, I don't know if it's still the same here, having a PhD was very, very important. And we purposely picked some people who were absolutely brilliant software developers who did not have credentials. And it was interesting to see the people within Google. Some people, as soon as they found out they didn't have any sort of credentials at all, would just ignore them and walk away. But other people would listen to what they had to say because they were universally saying very, very smart stuff just because they didn't have credentials. But it was really interesting to sort of parse the audience within that organization for, I care about fake credentials more than I care about what you're actually saying. And so I think that's the way to get to is to, say things so compelling that people don't care what your credentials are. They'll listen to you anyway.
In AI-assisted future, how do you see the software architecture rule will evolve?
Well, that's a great question. I wished I knew. If I did, I'd be rolling around in big fat stacks of money like Scrooge McDuck in the cartoons. Who knows? Especially with this, it's changing so incredibly fast. What we're learning pretty quickly is what a lot of us have predicted is that generative AI makes a terrible software architect. In fact, that's probably the last role in software it's going to be able to replace because software architecture, as I said, is about objective trade-off analysis. And generative AI is nothing but a big giant pattern matcher. And so to make it be good at software architecture decisions would mean that there have been thousands of identical software architecture decisions exactly like yours that other people have made in the past, so it can pattern match on them. But that's not true. In fact, nobody's software architecture problem is exactly like yours. And so it's now guessing and hallucinating. And that's probably not what you want in your architecture solutions. The actual best thing that we find to use it for, boundary conditions and what-if analysis. Here's my plan. Are there any problems or boundary conditions I haven't taken into account? It'll give you 10 answers. 6 or 7 of them will be meaningless or useless. 2 of them will be things you've already covered. And 1 of them will be like, oh, yeah, I didn't think of that. I should really apply that. And so that's actually taking advantage of the non-deterministic nature of LLMs is that they may suggest something that you never thought of at all. And so it's a good way to get that kind of what-if analysis. But don't trust it at all for any kind of trade-off analysis because we've actually tried this a lot with known solutions to problems. And even when it gives solutions to problems, it tends toward maximal complexity, not elegant simplicity.
I attended with you the training architecture as code, and we tried generative AI with fitness function.
Yep, that's something we've been using it for a lot as what we're calling an interpolator. Not an interpreter, not a compiler, not a transpiler, but an interpolator, because it's taking our intent and then figuring out for itself what our intent is. And so what we say with those kind of generated fitness functions is trust but verify. So always look to see, did it actually produce something that's producing what I want and not something wild and crazy. But that's also a use that we've been using generative AI for is to, and part of the idea of our book is to capture these architecture decisions in pseudocode and then use generative AI to produce concrete fitness functions, because many of the architects we work with aren't restricted to a single platform or technology stack. I have Java projects, I have .NET projects, I have Python projects, I have JavaScript stuff. And so having a single intent somewhere, like referential integrity or a certain amount of complexity, and being able to apply that across all these different projects and ecosystems is really nice by using generative AI to generate concrete fitness functions. So
I utilized the idea that I learned from you, the SDL, in more advanced thing, and it worked pretty well. So especially for architecture diagrams, by the way. So I used it for doing complete sequence diagram, which I may spend almost 45 minutes drawing it. He built it for me in 1 minute, but I just wrote the correct SDL for him.
Yep. So it turns out that, and this is one of those things that's obvious in hindsight, it's the second L. It's a language model. So it's really good at translating between languages like pseudocode and concrete APIs, or pseudocode and well-known diagramming techniques. And so it's really useful for that kind of generative work.
So do you recommend vibe coding? Do you see any warnings?
Well, yeah. So vibe coding is a very dangerous thing. Well, first of all, it depends on which of the 4,353 definitions of vibe coding are you currently using. Because vibe coding, more than anything else, indicates the problem, what Martin Fowler calls semantic diffusion. That when a term hits our ecosystem, everybody immediately applies their own definition to it and then assumes everybody else is using the same definition, which is almost never the case. So the original definition of vibe coding was this Andrew Karpathy blog post where he talked about, I wanted to build this little project and I didn't want to focus much on the details. I just wanted to get in this flow state. So I just sort of vibe coded. And so that's where the original meme came from. And he talked about building, in just a few hours. Basically, what he's talking about is so software development is part craft and part engineering. And what he's basically doing is say, I want to do all the craft part, but none of the annoying engineering part. That's really vibe coding. Is I just want the enjoyable parts of software, which is generating new stuff without the annoying problems. But of course, and he couldn't write these things. He published this blog about his vibe coded thing. And then a couple of weeks later, he wrote another blog that's like, I'm getting a lot of unusual traffic on my site and I don't understand what's going on. Can somebody help me out with it? Because, of course, he had massive security problems in this vibe-coded thing that he put out on the internet because he was paying attention to just the behavior and not all of the important things like security and scalability and performance and all those things. And so that's the danger in this idea of vibe coding, of, just ignoring all the engineering parts. Is great if you're just building throwaway things, but don't think you can build real software that way. And two, how much of the software do you build is something so small that you can build it and deploy it in 2 days? People in the real world build software that lasts for years and years and years, and you don't want to build the foundation for the future in as fast and throwaway a way as possible. You tend not to build buildings out of paper cups. You build buildings out of, steel rods and girders and, things like that. That's kind of what vibe coding feels like. But I just recorded another podcast, the Topologies Technology podcast, where my colleague Prem is talking about what they're talking about with vibe coding, particularly with the new agentic AIs, is actually trying to, can I build specifications to the point where I can actually build some of these validations into and have the agents go off and do some of these things for me, like, build fitness functions as part of, so why not build as part of my description for the behavior, build all these architectural constraints into it as well, and build me fitness functions as part of your coding. But now the problem you run into is that, and this is a problem that many people have talked about, the specifications are getting so complicated now that they're becoming waterfall design documents. You have to put so many details in these specifications. It's like, I could write the code faster than I could write this incredibly detailed specification that I'm just going to pass off to an LLM and have it set a few barrels of oil on fire to implement for me anyway. So, what's the real benefit here? So there's a trade-off there. But I think there is this idea, particularly with the way agents work now, of being able to generate chunks of code with protections and other validations, very much in the same way that we did this in the TDD and test-driven development in the Agile world, of building very small pieces and then check those in and get them integrated with continuous integration and then build other small pieces, but with robust validations, fitness functions and unit tests and those kind of things. I think supervised coding like that in the near term using agents is going to be something we're going to spend a lot of time on. But 6 months ago, that would not have been my prediction because the agentic stuff was not as powerful as it is now. So any prediction about how generative AI is going to affect the software development ecosystem ages like unrefrigerated yogurt. So,
For software architect to walk with the trend, what skills should he learn now?
The number one primary skills is trade-off analysis. Learn how to do trade-off analysis because every single piece is going to change throughout your career. We're going to change platforms and technology stacks and programming languages. I mean, 10 years ago, cloud didn't exist. 5 years ago, generative AI didn't exist. 10 years ago, we had one kind of database. It was a relational database. Now we have dozens of different kind of databases. Every single piece of your ecosystem is changing and evolving all the time. So the best piece of advice I can probably give is don't treat it like an equation to be solved. It's constantly moving thing through time. And so keep track of what's happening in the software development ecosystem. But I think it's really important, and this goes back to one of the things that we've always done at ThoughtWorks, and this gets back to the original theme we started with this podcast, is about engineering practices. One of the reasons that ThoughtWorks has been successful for so many decades now is that we understand good engineering practices. We actually created an open source, the very first continuous integration server, cruise control, was a ThoughtWorks project. When I was interviewed with ThoughtWorks, one of the people who were interviewing me was one of the creators of the in-unit testing library in the .NET world. So we have a long history of understanding good engineering practices and then being able to apply what innovations are happening in the software ecosystem, but still apply good engineering practices to them. So, for example, when user experience design became all the rage, the common wisdom in the software development world is, well, you have to let them build the entire user experience and then work on all the code with no feedback loop. And we said, nope, that's counter to our engineering practices. So we figured out a way to create smaller slices and build feedback loops for user experience design. Same when mobile development came out. Same for generative AI. So once you understand good engineering principles, it's easier to see how innovations like generative AI fit within the ecosystem. They're not these massive black swan events. It's just another change in the ecosystem. And then figuring out how to accommodate that, I think, is one of the keys, because change is going to keep happening. At least that's been my experience. And it doesn't seem to be slowing down any either. So that's also been my experience, that the rate of innovation doesn't seem to be slowing any. If anything, it's speeding up. So
I would like to end with one dilemma which we all face regarding the documentations, and also get your opinion about this, Neal. So we all need to have some documentation. At the same time, we know documentation will be out of date very soon. How can we solve this dilemma?
Well, with great effort. So one of the ways you can solve this dilemma is to don't produce extraneous documentation. It's just there for the purpose of creating documentation. This is part of the goal of ADRs and architecture decision records, is to capture just the context. And the entire purpose of an ADR is not, the end result is not to document it itself. It's to prevent yourself or some future version of yourself from having to go through the exact same trade-off analysis you had to go through to make this decision, because I need to revisit this decision. So it's really just a shorthand way of bringing all that stuff back into context. So that's the ideal use for something like an ADR. It's been my real world experience, though, that it's harder to get people to read ADRs than it is to get them to create them. People actually like creating ADRs because it's the excuse to sit down and work through all their rationale and show off their trade-off analysis and how clever they were and coming up with this decision and all that. But then when you make a new decision, I don't want to read a bunch of other people's ADRs, because, that's not fun. I'd rather go off and write some code and build some stuff. And so getting people to actually reuse them, I find, is tough. But this is like any sort of holistic documentation exercise. I've seen very few large organizations that did this well. There's a reason that there is a university degree called library science, because organizing things is hard and it's not trivial. And every developer I've ever met thinks it's trivial to organize and categorize things, but it's not. It's very, very difficult. And so I've never seen projects do that particularly well. It's always works best in a small scope. And so every project that I've ever been on has some sort of wiki or something like that has practical information, like what are the IP addresses for the test machines. And, it's just stuff like that you need to know as part of your development. those kind of hyper localized kind of data stores seem more useful to me than these kind of broad, holistic kind of decisions across the enterprise, for example. My hope for that is by building more of those as executable code, you're creating less of a documentation framework and more of a feedback framework. So if you could express those things in a fitness functions in a way that didn't break constantly because of changes in your ecosystem, then I think that's a better way to document things because it's executable. I always prefer executable documentation because this is the classic dilemma as you were talking about. Oh, look, there's documentation for this project. What's the first thing you look at before you open the documentation? Last change date. The last change date was a year and a half ago. Are you going to trust any part of that documentation for that project? You'd be a fool to trust that because you know it's completely out of date. That's the advantage of actual tests. Because tests, when they get out of date, they break and you have to fix them. So that's why fitness functions, unit tests, et cetera, anything that's executable is always better. The problem with that, of course, is that your project owner is not going to read fitness functions. ADL, our architecture description language, that's part of the purpose for that is, can you write it in pseudocode in a way that non-developers can understand it, but it can be translated into real code. So we'll see how successful we are as we get this book written. That's our next task. In fact, that's what I stopped doing to record the podcast today, is work on that book.
We will be waiting. And we will nudge you soon also. Neal, it's been a pleasure having you with us today. I really enjoyed this podcast with you. And also, I am awaiting for everything you deliver, especially on O'Reilly. By the way, Mark told me that you are working on right now in 2 books. I would like to ask about them.
Yep. One of them is Software Architecture Patterns, Anti-Patterns, and Pitfalls. We're writing that with Raju Gandhi. And then the other is the Architecture's Code book that I'm writing just with Mark. We're actually going to finish. Yes, both for O'Reilly. The Patterns book will be out probably mid next year. Architecture's Code will probably be late next year. We're more than halfway through the Patterns book, so it's coming along quite nicely.
Early version coming soon?
Early release are out for the Patterns book now and for the Architecture's Code book in a few weeks.
Perfect. Thank you, Neal, so much. If you have any final advice to the engineering teams today to deal with the challenges or something that you think it will be a challenge soon?
Yeah, probably my best advice is don't treat anything like it's the end of the world. It's just another change in the ecosystem. One of the advantages of having been around in this ecosystem for a long time is I've seen a lot of crazy changes. Nothing quite as crazy as the generative AI stuff, but enough to see that this is a difference in magnitude, but not in type. So this is just yet another one of these changes. I expect that this ocean wave will roll over us and there'll be yet another innovation. And the reason these come about is because changes in our ecosystem create new capabilities. Clever architects figure out how to utilize those capabilities to build new things. And so I don't see that changing anytime soon. So my probably best piece of advice is to always be on the lookout for how our ecosystem is evolving and how people are taking advantage of how it is evolving.
Thank you so much for the great advice. Thank you so much, Neal.
My pleasure.
And again, we have the whole pleasure having you today and wish you all the best in the coming books.
Thanks. It's great to be here.